So tightly coupled is something readily available in the cache. So there is the implementation of a cache. So loosely coupled is it may not be directly available in the cache, but on request you may get it. So MPI or message passing interface through which you can get the data whatever you that at that particular moment of time you want to compute. So that is what is meant by tightly coupled shared processor. So thread level parallelism is implemented at tightly coupled shared memory multiprocessors. For n processor needs n threads, so that on every processor you are running one or the other sequence of instructions. Thread is basically sequence of instruction or continuous sequence of instructions for that matter. So somewhere task level parallelism or thread level parallelism can be exploited. So you are somewhere after ILP stagnation, so you move on to the next level, task level, then or thread level, where you see some continuous chunk of instructions which can go into different processors. The amount of computation assigned to each thread is normally called as a grain size. So whether the grain is fine or coarse depends upon the application and how do you bifurcate or uh, formulate the size of a grain is again a issue that is not addressed as over here. But yes, so grain is what is running on individual processor as such. So normally it may be finer in nature whenever you are thinking in the perspective of cache kind of stuff. So threads can use for data level parallelism, but the overheads may overweigh the benefits. So data level parallelism is basically you are reading and reading out to the parallels simultaneously, but duplication and data integrity maintenance, yes, that adds to the complexity of the infrastructure. You have to provide that. How is a very big thing. So symmetric multiprocessor or SMPs, normally whenever you are imagining a multi-core, so it is the same processor duplications, the processor 1, processor 2, processor 3. So whenever you are imagining all are of similar kinds. Messages as such, or anybody wants to. Okay. Okay. Done. So symmetric ಅಂದ್ರೆ similar kind of processor, same processors will be utilized over there. So small number of course, shared single memory with uniform memory latency, or OMA kind of architecture. OMA is a uniform memory access. So what is uniform over here? So there is a shared cache. So all the processor, even though they may be having one or other, so basically private memory and with the tightly coupled memory, that is cache. So they are having their own caches, but there is a bus architecture through which you are accessing something shared. So but shared memory is again having its base. So the lower architecture is main memory, so something much faster. So maybe L3 of all the processor is shared, L2 and L1 are private, still private to the processor. ಆ ಥರ imagine ಮಾಡ್ಕೊಳ್ಬೇಕಾಗ್ತದೆ. So ultimately uniform memory access is whatever you are fetching from shared cache is having the same amount of memory latency. So how much time you are spending to access that. Distributed shared memory architecture or DSM. So basically this is limited by because the processor wants to read or write from the cache. ಇಲ್ಲಿಂದ ತಗೊಂಡು ಬರಿಬೇಕು ಅಥವಾ ಓದಬೇಕು ಮಾಡಿದ್ರೆ. So what limits this kind of SMP multiprocessor or the bus architectures with respect to multiprocessors is basically traffic. So individual processors, they just want to have the access to the shared cache. Maybe you are writing to some different locations at a given point of time, or read from different locations, but there is a huge traffic that starts limiting factor for the shared memory locations. Now what is the other architecture? Then you go for a NOMA architecture, so non-uniform memory access. Now instead of a simple bus, now the interconnects, there's a digital switch network kind of architecture. So something similar to COMA or the cache memory architecture. There is a particular network. So I can just showcase something for that. This one I just wanted to. Okay. So switched. So there are crossbar switch, or there is a processors, there is a memories, and how they interact is normally complex network that has to be established on the crossbar switch, omega switch network. So these are the different kinds of network which are being targeted. So you can just assume that there is a specific kind of network which promises fair transfer of data across the network as such. And why do you call it as a NOMA architecture or non-uniform memory architectures? Whenever you are imagining, say, zoom ಆಗ್ತದೋ ಇಲ್ಲ ಗೊತ್ತಿಲ್ಲ. Okay. So multi-core microprocessors, there is a processor and there is one memory over here, and you want to fetch the memory of the others. So there is no common shared memory as such as in case of a UMA architecture, non-uniform memory architecture. So every individual, so they have combined their own memory. So it is not only the caches now L1, L2 cache, here I will maybe L3 is combined together called as a shared cache. Now everybody is having their own private memories only. So whenever I'm reading and writing to my private memory, I'm much faster compared to whenever I want, or this particular processor wants to write something with respect to this memory architecture. So then normally that has to happen through the processor architecture or multi-hop, depending upon the network, whatever you are imagining. So grid or the crossbar switch, whatever the mechanism you are using, interconnect network you are using, through which the latencies go on varying. So whether you want to travel only the, maybe it is the nearest, maybe it's a far further, and so on. Non-uniform memory access and the latencies will start affecting the stuff. So how do you promise somebody who is expecting data should be available within a stipulated amount of time, or data coherency should be established within certain span of time, becomes a complex problem. So what is meant by cache coherency? Again, starting with the definitions. So we stated that data consistency of the data should be same across the different layers or the levels of the memory architectures. Whenever I say I am copying the one memory location, say in this case AX, to different processor individual memories as such. So whenever one processor writes into it, so either through write back or write through mechanism, whatever the mechanism you adopt, finally the data should be consistent from wherever you read it. So that's what is the intention. So maybe the address and the physical address or logical address, tag bits, everything, whatever the um, required stuff you are doing. So after all that, so some address 0x8000, if I say that, how you are fetching, whether you are fetching from the cache, whether you are fetching from the main memory, is irrespective. Say 8000 location has some data and that has to be displayed. So maybe local copy or actual copy, so from the actual memory or the main memory as such. So we'll see that why and how it is important and how it affects the performance of a processor, or the computation has integrity has to be maintained. Illonist clock cycles ಕೊಟ್ಟಿದ್ದಾನೆ, say time 0 1 2 3, and then the events that are happening. So timer 0 memory contains some data, so in this case it is 1. Now processor A reads X. So whenever it reads X, basically it goes for a cache. If I we will go to that explanations later part, but whenever he wants to read it, so he has to copy it from main memory. So memory contents of location X, now the content are copied to the local copy. So global copy to local copy, if I'm saying okay. In any case, shared memory agli to distributed memory. So directory protocols are just, you are storing that associated bits in a particular directory whenever you're operating. So memory blocks are assigned, and you check whenever you want to manipulate that, what is the status of that particular memory, and then operate onto a memory location. The directory based protocol. Snooping is whenever any updation happens with respect to that memory, invalidated, modified, shared, exclusive, so they are broadcasted to the bus, and every processor is normally listening to the bus, and he will modify the contents if the broadcasted content is available in your local copy, or update local copy ಅನ್ನೋದು ಬರ್ತದೆ. They are the strategies with respect to which you deal with respect to cache queries. So restricting myself to again to this example, what has happened is, so there was a memory read from processor and that has been copied and made available. And that means there was a cache miss, then there's a copy, then there is a cache hit. Processor A now has a content 1, which is now it starts operating on this location rather than the main memory contents. So whenever you are operating, so processor B also wants the same content, and some thread wants the data, same data. Now processor B wants to read, so because it's a read, so processor also reads from the main memory and copies it from the into his local copy, the cache processor contents for processor B. Processor A stores 0 into X. Now processor A writes into local copy. So whenever he is writing, he is making it write through. Write through is he has updated. So basically, what is meant by write through? Update all levels of cache. Fine. So what has happened? So it has copied the content, say 0 to right back ಅಥವಾ right through ಏನೇ ಹೋದರೂ ಸಹಿತ whatever the policies you are implementing. So right now we imagine a right through scenario, which is a costlier affair, but still it has updated the local copy, but now it also has updated the main memory contents. The consistency or the cache coherence has failed because B is totally unaware of what has happened to the memory location. So contents for the same memory location. Now for the processor B it appears to be 1, processor A it appears to be 0. No, there is a deviation or the cache coherence has been violated. So what is the ultimate aim of maintaining a cache coherence is maintaining same data, something of this sort. How do you want to achieve that, or how we make it happen? So all reads by any processor must return the most recent return value. So whenever you are reading, the most updated value has to be returned to a particular processor. Writes to the same location by any two processors are seen in the same order. So there is a serialization or sequencing operation that has to be followed with respect to the writes. Read can happen in any manner, but writes are to be serialized. So that's how we establish a coherence across the processors or nodes. Consistency, when a return value will be returned by a read. So uh, if a processor writes to a location A followed by a location B, any processor that sees a new value of B must also see the new value of A. So that has to be updated. All the other processors which are using them are to be updated, right? Or writes have to be serialized or sequentialized, so that the consistency has to be maintained. So what is violated over this location is, so processor B is totally unaware of whatever has happened to the content of that particular memory location. So that should not be happen, or the data should be transparent across the processors. Any processor that sees the new value of B must also see the new value of B. So if there is a dependency, whatever you are using, any application with respect to that has to see the data. So coherent of caches provide the what is meant by enforcing coherence. How do you make it happen? Movement of data, so that whenever write through or write back is the approach through which you are making that happen. Replication, so copy the contents to different hierarchy levels wherever they are required to maintain the consistency or coherence. Again, whatever the terminology I am using are interchangeably, but they have the separate meaning as per the slides as such. So cache coherence protocols, there are two protocols, again broadly classified. Directory based sharing status of each block is kept in one location. So whenever you are accessing, just see that it is as good as what has happened to that particular block, whether it is clean or dirty, it's invalid. So that will be seen at a particular location. So all the memory blocks will have their status stored at some directory. So that is what is meant by directory based protocol. Snooping is there is no centralized information about the contents of memory or what has happened. So every processor is listening to the broadcast message. So you are totally aware of the channel, or you are always listening to the media because something is happening onto the bus always. So you are well aware of the traffic, and wherever something changes with which really affects you, so then you respond to it and update as and when required. So each core tracks sharing states of each block, right? Snoopy protocol is a bus based protocol. Basically every processor, or the simplest protocol ಅಂತ ಹೇಳ್ಬೋದು. Limited number of processors, there is no connect kind of a complicated network kind of architecture is not there. A simple bus architecture is there, and every other processor or whoever wants to share the data from the shared memory is listening to that bus architecture. On write, invalidate all other copies. So processor 1, processor 2, processor 3, everybody is listening to the same location. If processor 1 writes something into a particular location, if processor 3 has a copy, whenever he is writing that, he is broadcasting that into a message. So some shared memory is manipulated, and if somebody has a copy, he also has to update that, because anyway it's a broadcast message. Now shared memory, simultaneously the processor B or whoever has a copy has to be updated. use bus itself to serialize. How does it happen? So you have to go for the bus mastery or bus arbitration happens, and with which you obtain a bus mastery, and whenever you broadcast, so that is you are given a higher priority, or and updation happens as per your commands. So mastery of the bus decides serialization. How they happen? So processor A reads X. Now processor is attempting to read a cache and it is not available in the cache. So cache miss happens for the X. They are available in the memory location. ಇಲ್ಲಿ 0 ಅಂತ ಇದೆ ಅಂತ ಇಟ್ಕೊಳ್ರಿ. So then after that contents of processor A cache. So it is able to read. So cache miss ಆಯಿತು. So then block transfer. So cache miss penalty ಆದಮೇಲೆ then the data is made available and processor is able to copy the contents of location X. Processor B reads X. Now again there is a cache miss for with respect to processor B. Initially it doesn't want it. Now it wanted to read that. So now whenever it reads, again it reads 0. Processor A writes 1 at X. So there is a invalidation of X. So basically what it has done is it has not returned the contents to the location B as such. It is just manipulating one bit of that local copy, invalid bit, so that whenever the processor attempts to read or write that particular copy again, it sees the invalid bit and hence it wants to obtain a fresh copy. So whenever it wants to read B next time, so it is not write operation, please note that it is a read, still a read operation. So whenever it wants to read, now again there is a cache miss because that memory was invalidated by the processor A because it has written or manipulated that memory contents. So that invalidation has gone as a broadcast. Processor B has noted that broadcast and it had the copy of that local copy of that content. It is just manipulating that particular bit, invalid bit interpret ಮಾಡ್ಕೊಳ್ತದೆ. So the valid bit is toggled, so it becomes invalid, and hence whenever it wants to read, or processor B wants to read the same location again, what happens is basically there's a invalid or there's a cache miss. Again you have to read it from the main memory. So on write, update all copies. So update all copies, whether you want to update simultaneously, that happens to the write through. You just are transmitting invalid or dirty bit, that is only you are writing. Whenever somebody wants to read that, or I'm operating onto that particular location, then it has to be with respect to cache miss ಆಗ್ತದೆ. Then you go ahead with respect to the execution. Snooping corresponds locating an item when a read miss occurs. So what is the location? Write back cache and the updated value must be sent to the requesting processor. So write back is basically your on read miss, you want to update the locations. All the hierarchies are written on write back. Right through you are writing through the hierarchies, first to the local copy, then to the global copy in some order. Cache lines are marked as a shared or exclusive / modified. Now he starts exhibiting certain bits reserved for how that particular memory location is being manipulated. So whenever you say shared, it is shared across. So no single processor is owning it. It's basically shared. So it is exclusive. So exclusive in the sense that one processor claims the ownership of that. So sometimes some memory locations, they have the other bit called as a O bit, called as a ownership bit. So whenever you say exclusive, that at that moment you are claiming that the particular memory location is yours, entirely yours. So you can do whatever you want. You can read and write the stuff. Otherwise, normally you are able to read. If it is invalidated, again you have to read from the lower memories as such. So after this, the line is marked as exclusive. Only that processor is able to manipulate and do the stuff with respect to that. So in what context we are studying them? If you can imagine, with respect to large computation, again whatever the chapter title was, this is a cache coherence is a different protocol, or the separate subheading for that matter. We are dealing with this title in the large scale computations. Whenever you are dealing with respect to that, ಯಾವ ಆ್ಯಂಗ್ಲಿಂದ ವಿಚಾರ ಮಾಡ್ತಿದ್ರೆ ಅಂದರೆ shared memory or data integrity maintains cache coherence protocol ಯಾವುದು locking. So carrier sense, level sense, atomic operations whenever imagine, so that between lock and unlock something is atomic, or it should not be interrupted, that has to run continuously whenever a particular processor wants to run in that particular mode. So then these things will pop up and come into picture. So exclusive mode, atomic operations. So no other processor should be disturb me whenever I'm operating onto that particular. So maybe count or counter, whatever the programs we have seen in the chapter subheadings as such. So these are the things again tabulated with respect to the read hit and read miss. Just take some time or take 2 minutes to glance through that. Just read them. So request, read it, and what happens down to the bus and what happens down to the cache. So again, it is summarized in a block diagram that is much easier to read or represent or by heart or memorize as such. But to make that happen, this was the first step. Address conflict miss. Okay. So whenever you are discussing modified, so owner has modified it, so it is readily available in the local cache. So whenever you are stating shared, so now there is a coherence that is coming into picture. So across two processors as such. Okay. Okay. I think go to that diagrams. So you want to try to, so whenever you are reading a particular contents of memory and that is invalid, then these are the stuffs or the arrow marks depict what are the signals put onto the bus as such. Then the states of memory are toggling between the invalid, shared and exclusive ISI, or most of the MESI ಅಥವಾ protocol ಹೆಸರುಗಳು ಬರ್ತಾ ಹೋಗ್ತವೆ. So right now with respect to Snoopy protocol is basically all the processors are listening to the bus. There is no directory kind of architecture where you are storing the validity of the bits related to that particular memory block as such. There is no centralized information with respect to memory. So whatever happens through the bus or broadcast messages. So you have to listen and you have to update, or the particular processor has to listen to that particular broadcast and gets it the things updated. So on CPU read miss, place a read miss on the bus, and if it is available, then CPU read it. So if it is shared, then place invalid on bus. CPU write happens, write back block. So now you get the data. That is how. So CPU read miss happens. Place read miss on the bus, then just transact, or what is your the arrowheads showcase that what is happened, or the same entire table is summarized as such. ನನ್ನ ಹೇಳೋ ಕಷ್ಟ ಆಗ್ತದೆ. Okay. Or framework is stating there are bits stating invalid. The current contents of the memory with respect to any processor's local cache is stated as invalid. Whenever you are fetching some invalid line from the cache, so basically you are generating a read miss write miss. So read miss ಅಂದ್ರೆ that is not the current content or copy of that, so that has to be copied from the main memory. So whenever you are going for that main memory, so only you have the copy or somebody else also is sharing that particular memory is indicated by shared bus, shared bit. So that means the updation has to be shared across two process or whoever are contending for the particular locations as such. So the shared ಅಂತ ಆಗ್ತದೆ. So shared ಹೋದಾಗ read only because writes require exclusive permissions. You want to operate onto that exclusives. Most of read write ಅಂತ ಬರೆದಿದ್ದಾರೆ, but rights require exclusive permissions for that point, and they are broadcasted. So and again, if you are having that shared copy, either you invalidate or update. So invalidate normally creates whenever you are reading that will ಏನಾಗ್ತದೆ, read miss ಆಗ್ತದೆ, then you copy the stuff. Otherwise that is with respect to the uh, write back approach. Write through approach ಅಂತ ಹೋದ್ರೆ, so you update all the levels simultaneously, so all the local copies have to be updated. And there is a pros and cons with respect to individual approaches. So how many times it has happened, or there are more pending writes or more pending reads, if I say see that, then what happens to write back, right through. So there is a penalty or more bus transactions, or there is more traffic. So what is important is MSI. M is for modified, S is for shared, and I is for invalid. And this is a protocol. So operations are not atomic. So example, detect miss, acquire bus, receive a response. Normally that creates a problems whenever the things are not atomic. Atomic in the sense the things can be interrupted. So before you complete that transactions, whether you have updating the memory locations or the contents of that particular memory, or you are creating a copy, in between you are interrupted, and hence that causes the data uncleanliness. So it creates a possibility of deadlock and races. We'll see that what is meant by deadlock, live lock, and like, the starvation. So anybody, if you want to elaborate upon deadlock, you can just go ahead. ಹೇಳ್ತೀರಾ ಯಾರಾದರೂ? So if you are competing for more two resources, one thread wants more than one resource or more than one memory locations, and it has acquired one and it is waiting for somebody else. So the task one wants R1 and R2, task 2 also wants R1 and R2, but task 1 has acquired R1 and wants to run to the completion. Task 2 has acquired R2, it wants to run to the completion, but it is waiting for R1, then that is waiting for R2. So there is a lock, and they wait for indefinitely or infinitely, then it is a deadlock. Live lock, you are not competing, you are not withdrawing yourself anyway, so you are creating a live lock. So waiting indefinitely creates a live lock. So that special class creates, you are making all other processors to starve, and that is nothing but a starvation. Just to brief at this juncture or slide as such. So one solution, processor that sends the invalid can hold bus until other processors receive the invalidate. At least if you are not transacting the entire cache lanes or the want to support the read misses, at least let them know that the contents are no more valid. So there is a updation, or normally memory, some memories will have a dirty bit, so that is manipulated. The memory manipulation illa antandru, that line is no more consistent, so it is invalid, so you have to read from main memory again. So at least transmit that invalid or broadcast that invalid stuff. So you can add exclusions or the exclusive state, so that only one processor is operating onto a particular memory location, so that atomic operations are supported. So whenever you say that this piece of code has to be executed by only one processor at a given point of time, or there's a critical section or exclusive section has to run, or that variable has to be updated by only that particular processor. There is no parallel threading you are expecting at that location. In that sense, you are want to go for the one more bit of the indicating that ownership of that particular memory location. So prevents needing to write invalid on a write. So whenever you are saying that you are exclusive using that, You need not. Everybody knows that that memory belongs to you, and they don't have the copy of that. Whenever you release them, then you update invalidation for them. So it is a ownership state. So shared memory bus and snooping bandwidth is a bottleneck for scaling symmetric multiprocessor. What happens is if more than one processor, two processors are competing under one bus ಇರ್ತದೆ. So in the same bus, you are sending all the informations. So there is an information rush or traffic jam, and hence that is a bottleneck for scaling. So scaling is so NAC processor in the 14 processor. Whenever you increase the number of processor, generally there is a more communication happening with respect to the more number of processor that creates a bottleneck. So this becomes infeasible for implementation as such. So duplication of tags placed directly in outmost cache. So use crossbar point-to-point networks with the bank memory that is interconnected. How would you interface that network as such? So AMD Opton memory directly connected to each multi-core chip with the NUMA-like organizations. Whenever you see NUMA-like organizations, there are two levels of memory. One almost immediate, maybe L3 cache is implemented as a shared memory architecture, and the remaining are the other memory, shared memory, maybe RAM or any other somewhat faster than RAM architecture ಇರಬಹುದು. So that is two types of access times or latencies with respect to memory access is faced, and hence it is called as a NUMARC or non-uniform memory access. Implement coherence protocol using a point-to-point links. So that crossbar space 2 cross 2 or whatever the crossbar space or omega switch ಈ ಥರ networks ಬರ್ತದೆ. So choose one among them. Use explicit acknowledgements to order operations. So serialization of writes is an important aspect. So he is using a different terminology for that matter, so that you acknowledge that whatever the development has happened with respect to one local copy is globally transmitted, at least at the stage of invalidation. If not the complete updation of that complete copying of that contents to other locations, at least invalid antu ಹೋಗಲೇಬೇಕು. Coherence influences cache miss rate. So true sharing misses, write to shared block, transmission of an invalidation that has to be broadcasted, read an invalidated block. So whenever you want to read it or whenever you want to manipulate or maybe read or write to that particular block, processor 1 has written something to that. Now if I say that it is exclusive copy, that it has owned it, so it has manipulated, no problem, but it has broadcasted invalid message. Processor 2 also had a copy of invalid, and through right through what it has done is it has copied the content to the main memory as well. So whenever processor 2 wants to read that same location, because it sees invalid bit in the memory locations or the local copy, so now there is a read miss, then it has to copy from the main memory, and hence the data consistency can be achieved. Read an unmodified word in invalidated block. All sharing misses that normally happen because only one particular block may be invalidated, not entire line, but now you are reading entire line as such, entire block or entire line of that invalidation. So again, some benchmarking. I'm not sure whether that or file memory access as real cache access, instruction execution. So L3 cache in MB, as you increase this, what is happening to the instruction execution or cache access, memory access. So if I can just want to bifurcate these three. So somewhere you are reducing the memory accesses and more data is readily available, and initially there was a so execution time is reduced drastically or performance is enhanced. So that is what is ultimately required for that, but there is no appreciable changes with respect to the ಎರಡರಿಂದ ನಾಲ್ಕು ಅಥವಾ whenever you are jumping from 2 4 8, so almost you see the things are almost same. Same memory access has been reduced whenever you make it 4, but 4 to 8 and 1 to 2 there is appreciable change with respect to memory access. It's a drastic reduction. 2 to 4, 4 to 8, whenever you are seeing that, there is some optimal cache block size which has to be decided, maybe 4 MB 2 MB. That's how I can comment about or reading the graphs as such, even though I'm not sure about what is PAL code he is stating about. Some execution code or benchmark code maybe, because I'm not reading that chapter directly. Okay, so true sharing, so false sharing, unrequired line sharing as such. Then compulsory miss or capacity miss that are happening with respect to memory cycles, they indicate or create the memory hazards or slow down the entire performance as such. It's because of that memory cycles per instructions processor count unit with respect to again sharings. What has happened, true sharing is really increased with respect to increase in the cache size as such. So in this again block size with respect to the increased number of points misses per thousand instructions. So now he defines what is the class of threads of the how much connectivity that with respect to somewhere spatial locality if you can think of, that is what is indicated by the graph research. True sharing, false sharing, what is the compulsory and capacity versus conflict misses. What has happened to them? So true sharing has been reduced. So that means you start reading unnecessary bytes as you increase this number of bytes as such. So false sharing definitely has to be increased. So ಇದು ಕಡಿಮೆ ಆದರೆ ಜಾಸ್ತಿ ಆಗಬೇಕು. But the rates you can see that the true sharing is drastically reduced, but false sharing is almost stagnated if I can see from the graph as such. Whatever the um, algorithm he has simulated the stuff. So just to benchmark or classify, they were nowhere directly related for seventh chapter or what was that, large scale computing. So directory protocols, as we have stated, there is a directory which keeps track of every block, which a cache access can have each block, dirty status of each block. So there is no invalidation, local copy invalidation. You are stating that that is being manipulated by one or the other person, and hence you are putting a dirty bit into the local copy. So implemented in L3 cache, normally the direct protocols are implemented in L3 cache. Bit vector size is equal to number of cores for each block in L3. So that is how do you form a directory, that is being stated over there with respect to the number of cores. Not scalable beyond shared L3. So L3 is the last. So whenever you purchase a CPU or for that matter, you can see that L1, L2 and L3 implemented in a distributed fashion. Again, you can see that there is a directory associated with every memory, and memory access happens to the interconnect networks. So it's local, and the other may be global. Global in the sense belongs to somebody else as such. More privates. So for each block maintain a state. So whenever you are dealing with the cache, basically you are dealing with the cache line or cache block. So the transaction unit or currency is basically block. So it is shared one or more nodes have the block cached value memory is up to date set of node IDs. So whoever are sharing it, so then uncached, say modified, exactly one node has a copy of the cache block value in the memory is out of date. So owner node id, somebody has modified and that is indicated that he has modified it, and the remaining persons who are having the unclean cache has to update that. So you are just indicating the status of that particular memory locations. So directory maintains block states and sends invalidation messages. So even here invalidation message is sent if at all they are reading it. Otherwise, anyway, it's readily available with respect to the directory structures or directory bits. ಅಲ್ಲಿ ನಮ್ಗೆ ಸಿಗ್ತಾ ಹೋಗ್ತದೆ. So just analyze or read this particular stuff, and then I think we get back in next class. Read miss, read, write miss, so on. Note ಹೋಗಿ. Next class I will finish this chapter. Say few more slides, maybe 33 slides are there. Another 10 we finish off this slide. And later part we have to move on to the blue gene. So blue gene is a case study with respect to whatever we have studied till now. After that, what was my plan was 30 minutes of arithmetic circuits. So parallel. If somebody is prepared or what is your schedule, who wants to deal with what, please share it with me. Okay, then take your time to read this. So exclusive honor or E bit or O bit will be there. So effect to Messi or Mossy protocol. Mossy ಅಂತಂದ್ರೆ ownership bit ಅಂತ ಬರ್ತದೆ. Messi is exclusive operation onto that particular directory. Invalidate bit is basically that cache line is invalid. That happens with respect to your TLBs, the transaction local site buffers, or whatever the caches are holding right now. That is invalid. So that ultimately creates a cache miss. From the remote access, invalid shared copy of data at address A. Fetch. So fetch the block at address A and send it to its home directory. So change the state of A in the remote cache as to shared. So earlier it's again local copy to one or the other processor. Now that was normally if nobody was requesting that particular data, it was in exclusive mode unless it is stated under, because that particular processor is the owner of that particular block and he reserves the rights. So whenever that happens or the transaction happens, so you switch to the shared mode. Okay, then so fetch and invalidate home directory. What happens is whenever you want to fetch it from the home directory, so it is available in the remote cache. So destination cache, fetch block address and send it to the its home directory, invalidate the block in the cache so that you have the most updated data. So the cache miss happens and then we have the data updation. So data value reply, again as we have stated, so most of the steps happen through the crossbar switch or the any other interconnect network mechanism that is happening. So whenever they are happening, they have to travel back with respect to the requests that are being made to the home directory, and the data ownership changes from exclusive to the shared model change ಮಾಡ್ತಾ ಹೋಗ್ತಾರೆ. So this is how the transaction, again it's something similar to your snooping protocol, but except the fact snooping is you are listening to the bus directory, you are storing them to the separate locations or directories in additional memory locations directly just to state the status of every individual memory location as such. This was absent in snooping protocols. Otherwise, diagrams almost looks the same. So these diagrams are not there in your appendix as such. Maybe you can refer to the chapter 3 or 4. So again, I don't remember with respect to the uh, fourth edition. So multiprocessor communications of these protocols are discussed over there. So if you have an insight into that particular chapter, then you can read that I.7 more easily, or you can understand that particular stuff, and hence that compelled me to go to this particular chapter slides, though directly not visible in your syllabus as such. Okay, then I think we will discuss further in the next class. So, any doubts, keep posted, and I have shared the contents of so arithmetic circuits. So, if you are interested in implementation, and then Israel Korean is a elaborative study with respect to arithmetic circuits as such. Want to restrict yourself with respect to the chapter or title, then go with the Patterson. So that maybe Appendix J is about that arithmetic circuits. So that is directly mapped to your syllabus. And please let me know how you want to handle that arithmetic circuits. So your schedule or who wants to handle what. So done then.